Hello friends, welcome to Power Electronics. Today we will discuss the single phase half wave circuit with RL load. As in the previous class we have discussed only with R load and we have observed the output voltage and also the RMS. Here as you can see in the figure that Vs is the supply voltage, that is Vm sin omega t, where T is the thyristor, Is is the supply current, and the voltage across the thyristor is Vt. Also we can see the load current I naught with the load, that is RL here. The voltage across the load is V naught. We will observe this by making the thyristor to conduct and see what changes we observe in the graph. As you can see, this is the sinusoidal waveform and we will check out what output voltage we get. So after the firing angle alpha, that is for delay of angle alpha, we have triggered the SCR at this firing angle. At here we have triggered it. So what we observe that there is gradual increase in the voltage. Here it increases, rises, and it reached at a point of 0 at pi. At pi instant it reaches the 0. But if you look at the load current, it rises here and reaches a point at the instant pi it is not 0. That means voltage is 0 but current is not equal to 0. As you can see, when we apply the supply voltage, current starts flowing from this path and starts passing through this thyristor. This act as a short and then current flows through R and L. Inductor is charged with the polarity plus minus. So this is how it works. At that point, at the pi instant, what we observe that the current is not 0. This is because of the inductor. Inductor do not allow the sudden change in the current. It has a property of it. So at when the cycle changes, here minus, here it is plus. The minus is across the thyristor. So we have applied the negative voltage across the thyristor, but still the current is not 0. Voltage is negatively applied across the thyristor but current is not 0. It required some time to reach a point 0. So we called it at a beta. This we all called as a beta. Beta is called an extinction angle. Here you can see beta is called an extinction angle. Beta minus alpha. So what here is alpha? Alpha is the delay time. So we minus it, we will get the value how the thyristor will conduct. So this all is called as beta. When we minus the alpha, we get a value gamma, that the thyristor is conducting at that period of time. So during the negative half cycle, when the thyristor turn off, you can see this is 0. Also you can see the voltage is still 0. So when we minus this waveform, that is source waveform, with this Vs is the source waveform, we minus with the output, what we get? We get only the firing angle here, alpha. This only alpha we got. This is eliminated here because the thyristor is short at that particular point of time. Here it is so 0. So what we have observed, because here due to inductor this current is not 0. This is the change we observed from the R load. In R load there is no change because there was no inductor, so it easily get 0. Voltage is also 0, so current was also 0, but here the current is not 0. As you can see in the negative half cycle, it do not conduct. Again the same process repeats after a alpha angle. At the instant after a delay of alpha, when it is triggered, we can observe that there is gradual rise, then it did not decay to 0 here, but current here has some kind of value, so it required some extra time. That is why we called beta must be greater than pi here. So same we got in the waveform. All waveforms are same after that. So what we have to we'll observe from that, here the load current I naught. The load current I naught consists of two components, that is one steady state and other transient. When we apply here KVL across this circuit, what we observe that minus Vs plus here minus Vs plus here Vt voltage across the thyristor, plus we observe that IR I naught into R plus L di by dt. So if we take the voltage other side, Vs equal to I naught R plus L di by dt. So after applying that, here Vs equal to I naught R plus L di by dt, we apply Laplace transform to this. Here the value I naught, if you can see here the value I naught, this I naught, that is load, has two components, one is steady state and other is transient one. How do we calculate the steady state? It is Is equal to Vm by R square plus x square sine omega t minus alpha, where the RMS current and voltage. So we here the RMS current Is lags by Vs. So transient component It can be obtained from free force equation, that is RIT, that is plus L di by dt equal to 0. Here we will calculate the value of It, that is AE R by LT, by applying the Laplace transform. So that load current consists of two components, that is steady state and transient. Vm by Z sin omega t minus phi plus A e raised to power R by L t, where Z is the impedance, as we know that is R and L. So under root of R square plus X square. So if you look at here, what values we have to remember? We have to remember the output voltage. I have already discussed how to calculate the output voltage average value, that is area upon the total time period. Whatever you got the area here divided by the time period, the area is Vm sin omega t, time period is 2 pi. So when we, and range is from alpha to beta, as you can see the thyristor conducts from here alpha to angle beta. So its range is alpha to beta. Then we integrate it, we get Vm 2 pi cos alpha minus cos beta, which is different from the R load. Also to calculate the RMS value, that is root mean square. First of all you square that Vm sin omega t, you make this square, then you set its range and the time divided by its time period, then you take its under root, then you get the value Vm under root 2 under root pi beta minus alpha 1 by 2 sine 2 beta minus sine 2 alpha under root. This value, this we called that average value and RMS value. You have to remember these values by heart, because in exam you won't get more time to solve the numerical, so you have to remember these both values. Also you can easily remember the graph, and you can, if you know how to calculate the average and RMS value, you can calculate it very easily. So thank you very much. We will discuss numericals in the next class.